Take an ordinary red laser pointer and shine it through a single slit cut thinner than a human hair, and something happens that quietly breaks the very first thing anyone ever told you about light. You expect a single bright line on the wall behind it, a simple shadow of the slit carried forward. Instead, you get a row of bright and dark bands, stripes of light with clean gaps of pure darkness carved between them, as if the light had been sorted into place by a rule nobody mentioned. But here is what the simple story leaves out. Turn that laser down until only one particle of light crosses the room at a time, alone, with nothing anywhere near it to interfere with, and the bands still build themselves, dot by patient dot. One grain of light, entirely by itself, arrives as though it had quietly traveled every possible path at once and weighed them all against each other. So how can a single photon be everywhere at once? Get comfortable and hit subscribe if you're new here, because by the end of this, the calm straight beam of a laser pointer will never look quite so simple again. Now, let's slowly ease into this. Part 1. The pattern that should not be there. There is a small experiment you can set up on a kitchen table, and it quietly breaks the most obvious thing you believe about light. You take a laser, the ordinary kind, the sort that throws a single clean red dot onto a wall. You place a thin barrier in front of it, and into that barrier you cut a very narrow slit, a slot far thinner than a hair. Then you let the light that squeezes through the slit fall onto a screen a few steps away, and you turn off the room lights, and you look. Your intuition already knows what should happen. Light travels in straight lines. That is the first thing anyone ever tells you about it, and it seems beyond argument. Sunlight comes through a gap in the curtains as a straight shaft. A flashlight throws a straight beam. So the light passing through your narrow slit should paint a single narrow strip on the screen, a bright line that is simply the shape of the slit carried forward. One slit, one line. That is the sensible expectation, and it is wrong. What you actually see is a row of bands. There is a broad, bright band sitting in the middle, and on either side of it there are more bright bands, each one dimmer than the last, fading as they march outward. And running between those bright bands are lines of complete darkness, places where no light lands at all. The light did not stay in its lane. It fanned out, and as it fanned out, it somehow organized itself into stripes, brightness, and darkness alternating, order emerging where you expected a simple smear. Physicists call this single-slit diffraction, and the row of bright and dark stripes is called a fringe pattern. It has been known for a long time. It is not controversial, and you can reproduce it this afternoon. But familiarity is not the same as understanding, and I want you to feel, for a moment, how strange it really is. Light aimed straight through a single opening arrives at the far wall carrying a pattern. Where did the pattern come from? There was one slit. There was one beam. Where did the darkness come from? Those clean lines where the light simply refuses to be. Look a little closer, and the pattern has structure worth remembering, because everything we do later will come back to it. The bright band in the center is the widest and the most intense by a comfortable margin. And here is the detail to hold on to. That central band is almost exactly twice as wide as each of the smaller bands beside it. The side bands are all roughly the same width as each other, but the middle one is double, 2 to 1. Keep that number somewhere in the back of your mind, because by the end of this, it will stop being a curiosity you noticed and become a number we can predict from first principles. It helps to compare the light with something ordinary, something that behaves the way you expect. Imagine spraying a fine mist of paint through the same narrow slit at the same wall. The paint droplets are little particles, and they travel in straight lines, and most of them that make it through the slit land in a single narrow strip directly behind the opening, with a soft blur at the edges where a few droplets clipped the sides. Narrow the slit, and the strip of paint gets narrower, exactly as common sense demands. there are no bands. There is no darkness carved into the middle of the spray. There is just a stripe, thinning as you thin the gap. That is the behavior of ordinary particles, and it is what you would swear light should do as well, because you have been told your whole life that light travels in straight lines, like a hail of tiny bullets. The paint obeys, the light does not. And the gap between what the paint does and what the light does is the size of the mystery we are chasing. Notice, too, that this is not some fragile effect that only shows up under laboratory perfection. You have almost certainly seen its cousins without knowing what you were looking at. The coloured sheen on a soap bubble, the rainbow glint off the underside of a compact disc, the faint halo around a distant streetlight seen through a misted window, the soft fringing at the edge of a shadow cast by a sharp blade in bright sun. All of these are the same phenomenon. Light arriving somewhere it should not, and cancelling somewhere it should not, arranging itself into brightness and darkness by rules that a simple straight-line picture cannot supply. The banded pattern on our wall is just the cleanest, most stripped-down version of something the world is quietly doing all around you, all the time. We have only pinned it down in a dark room so we can stare at it without distraction. Now imagine we do something more careful than just looking. Imagine we take a small light meter and we slide it slowly across the pattern, from one edge to the other, writing down how bright the light is at every position. When we plot those measurements, brightness on one axis, position across the screen on the other, we get a very particular curve. It rises to a tall peak in the center, drops all the way down to 0 at the first dark band, climbs to a much shorter bump, drops to 0 again, climbs to an even shorter bump, and so on outward, a tall spike, surrounded by a series of shrinking hills, each separated from the next by a point where the light vanishes entirely. That curve has an exact mathematical shape. It is not approximate, it is not fuzzy. Reproducing that precise curve, and understanding why it looks the way it does, is the whole quest we are setting out on tonight. You may have heard the standard answer already, and it is not wrong, it is just incomplete, in a way that hides the real mystery. The standard answer is that light is a wave. Waves, when they pass through a narrow opening, spread out on the other side and interfere with themselves. Where two parts of the spreading wave arrive in step, they reinforce, and you get brightness. Where they arrive out of step, crest meeting trough, they cancel, and you get darkness. This is genuinely how the pattern is usually explained, and as a description of ripples on water, it is perfectly good. The problem is not that it is false. The problem is that it quietly assumes light is a smooth, continuous, spread out thing, and light is not only that. Because light is also made of particles. It comes in tiny, indivisible packets of energy called photons, individual grains of light, each one whole and countable. A dim glow and a brilliant floodlight differ only in how many of these packets they pour out each second. And this is where the wave story starts to strain, because a wave is a spread out, communal thing, and a photon is a single, lonely speck. If the pattern on your wall is really about one part of a wave interfering with another part of the same wave, then what happens when there is only one photon crossing the room at a time, with nothing else anywhere near it to interfere with? That is not a rhetorical question. It is something you can actually do, and people have done it, and the answer is where the ordinary explanation quietly falls apart. So before we can understand how light builds these bands, we have to shrink the experiment down until only a single grain of light is in flight at any moment, and see whether the pattern survives the loneliness. Part 2. 1 grain of light at a time. Let us turn the laser down. Not off, just down, dimmer and dimmer, until the beam is so faint that the photons are no longer pouring through in a flood, but trickling through one at a time. We can make a light source so weak that, on average, a single photon crosses the apparatus, passes the slit, and lands on the far side before the next one is even released. Minutes can go by between arrivals. At any given instant, There is exactly one grain of light somewhere between the slit and the screen, and the rest of the room is empty of light entirely. There is nothing for that photon to interfere with. It is alone. To catch where each lonely photon lands, we replace the screen with a detector sensitive enough to record single photons, a grid that lights up one tiny point every time one grain of light arrives. And then we simply wait, and we watch the points accumulate, one at a time, like the first slow drops of rain on dry pavement. At first it looks like nothing. The first photon lands somewhere, and it seems random. A point here, a long pause, a point over there, apparently unrelated, another pause, a point somewhere else again. If you watched only the first handful of arrivals, you would swear there was no pattern at all, just light scattering onto the wall wherever it pleased, each photon landing in its own unpredictable spot. Each individual grain of light gives you no hint of order. It arrives as a single dot, in a single place, exactly as a particle should. But keep waiting. Let the dots accumulate. 10 photons, then 100, then 1,000, then tens of thousands, each one arriving alone, each one landing at a single unpredictable point. And as the dots pile up, something begins to surface out of the randomness. The points are not falling evenly. Certain stripes on the detector are collecting more and more dots, growing crowded and dense, while other stripes stay almost bare, catching almost nothing. And if you let it run long enough, the picture that assembles itself out of thousands of individual, one at a time, apparently random arrivals, is the exact same banded fringe pattern. The bright central band, twice as wide as the others, the fading side bands, the clean dark lines in between. Sit with how strange that is. Each photon went through alone. Each one was a single indivisible grain, with nothing else in the apparatus to meet or mix with. And yet, collectively, they arranged themselves into an interference pattern, arriving often where the bright bands are, and almost never where the dark bands are. The pattern was not built by many photons pushing against each other, because there was only ever one photon present at a time. The pattern was somehow built into the behavior of each single photon, on its own. This is the thing the simple wave story cannot carry. If the darkness in the pattern comes from one wave cancelling another, then what cancelled the lonely photon at the dark bands? There was no other wave. There was no other photon, and yet that single grain of light still, somehow, knew to avoid the dark stripes and prefer the bright ones. It behaved as though it were interfering, but there was nothing else there for it to interfere with. The only thing left for it to interfere with was, in some sense, itself. Let me sharpen the trap the older picture walks into, because it is worth feeling exactly why the obvious explanations fail one after another. Suppose you insist the photon is really a tiny spread-out ripple, a little smear of wave that oozes through the slit and interferes with its own edges. That would explain the pattern, but it cannot survive the arrival, because when the photon lands, it does not arrive smeared across the detector. It arrives at one single point, all of its energy delivered to one tiny spot, whole and undivided, the way a struck bell rings at one place, not everywhere at once. A spread-out ripple does not deposit itself as a single dot, so the smeared wave picture dies at the moment of detection. Suppose instead you insist the photon is a simple little bullet that went through the slit along one definite line and landed where that line pointed. That picture survives the arrival beautifully, one bullet, one dot, but it cannot survive the accumulation, because bullets fired through a slit build up a single stripe, not a series of bands with darkness carved between them. A simple bullet does not know to avoid the dark fringes, so the bullet picture dies at the moment the pattern appears. Each simple story explains one half of what you see and is destroyed by the other half. What the photon actually does is refuse both stories at once. It travels like something spread across possibilities, sampling the whole space between the slit and the wall, which is why the pattern forms. And it arrives like a single, indivisible grain, delivering itself to one point, which is why we can count the dots. It is not that we lack the cleverness to decide which picture is right. It is that neither picture is right, and the truth is a third thing, that our everyday words for wave and particle were never built to hold. For a long time this was where the story stopped, at a shrug and a paradox. What Feynman offered was a way to keep going, a way to actually calculate the behavior of that third thing, and it starts by taking the strangest possible stance toward the question of where the photon went. Notice also what we cannot say. We cannot say the photon is secretly a little spread-out wave that goes through the slit as a smooth ripple, because when it arrives as a single point, a single localized hit on the detector, whole and undivided, exactly like a particle. And we cannot say it is a simple particle that took one definite path through the slit, like a thrown pebble, because a thrown pebble does not build up an interference pattern. It is both countable, like a particle, and patterned like a wave, and neither picture, by itself, is enough. For a long time, this was left as a kind of uncomfortable slogan. Light is both a wave and a particle, people would say, and you were meant to nod and accept the paradox and move on. But a slogan is not an explanation. Saying that light is somehow both things does not tell you how a single photon, released alone, decides to land where it lands. It does not let you calculate that precise brightness curve, the tall central peak, and the shrinking hills. It just names the mystery and asks you to stop looking at it. What we want is not a slogan. What we want is a method, a way of actually computing where a lone photon is likely to arrive, one that takes the particle seriously as a particle and still reproduces the pattern exactly. We want to be able to point at any spot on that screen and say, with real numbers, this is how likely the photon is to land here, and have those numbers add up to the fringe pattern we measured. And there is such a method. It was built by a physicist who was famous for refusing to accept a slogan when a real explanation might be found. A man who liked to strip away the mystical language and ask, plainly, what is actually going on here? His answer was one of the strangest and most beautiful ideas in all of physics. And at first, it will sound less like an explanation and more like a provocation, because to explain how a single photon builds a pattern all by itself, he did not give the photon one path through the slit, he gave it all of them. Part 3. The photon takes every path. Richard Feynman had a habit of asking the most obvious question and refusing to be talked out of it. When faced with a single photon that somehow builds an interference pattern all by itself, most people asked which path the photon took through the slit, and then tried to explain the pattern in terms of that one journey. Feynman did something else. He suggested that the question itself was the mistake. Do not ask which path the photon took, he said. That question has no answer, and reaching for one is what traps you. Ask a different question, a question you can actually answer. Given that a photon starts here and is detected there, what is the probability that it makes that trip? That shift sounds small, but it changes everything. In our ordinary world, if you throw a ball from one point to another, there is a fact of the matter about the path it followed. The ball had a position at every instant. You could film it. In Feynman's approach to the quantum world, you stop assuming there is such a fact. You stop pretending the photon has a single secret history that you merely failed to observe. Instead, you ask only about the beginning and the end. Point A where the photon is born, and point B where it is caught, and you build a way to calculate how likely that journey is. And here is how he proposed to calculate it, and this is the idea that will either sound absurd or beautiful, and I hope by the end it sounds like both. To find the probability that a photon travels from A to B, Feynman said, you must consider every possible path between them, not the straight one, not the most likely one, every single one. The straight path from A to B, yes, but also the path that swings wide to the left, and the one that loops far to the right, and the one that wanders up toward the ceiling before coming back down, and the one that takes a lazy curve, and the one that zigzags. Every conceivable route the photon could take, no matter how ridiculous, is included. Each one of them contributes to the answer. I want to be clear that this is not a figure of speech. Feynman was not saying, imagine as if the photon could take many paths. He was saying, to get the right answer, the correct answer that matches every experiment, you must add up a contribution from every path, as though the photon genuinely explored all of them at once on its way from the slit to the screen. The photon does not choose, it does not pick the sensible route and discard the rest. In the mathematics, all the roots are present, all the roots count, and the final behavior is what you get when you add them all together. Say it plainly, because we are going to return to this sentence again and again. Light takes every path, and only the agreement survives. Every route is taken. What we finally see on the wall is not any single journey, but the sum of all of them. And as we will discover, most of those journeys quietly erase one another, leaving behind only the places where they agree. Hold that sentence. It is the spine of everything that follows. It is worth pausing on how much this asks you to give up, because the size of the sacrifice is the size of the insight. Every explanation of motion you have ever accepted rests on the quiet assumption that a moving thing has a location at each moment, a definite where, tracing a definite line through space as time passes. That assumption feels less like a theory and more like a precondition for thinking at all. And Feynman is asking you to set it down, not because he is being difficult, but because holding on to it is what makes the single photon impossible to understand. The moment you demand that the photon had one real path you did not happen to see, you are stuck, because no single path can produce an interference pattern. Only by releasing the demand, only by refusing to grant the photon one secret history, does the calculation become possible. The strangeness is not a flourish. It is the price of admission, and the theory pays it honestly. And I want to head off a natural misreading, because people often hear all possible paths and quietly downgrade it to something tamer, like the photon probably wobbles a bit around the straight line. That is not the claim. The claim is genuinely every path, the straight one and the one that detours past the moon and comes back, the one that spirals, the one that goes backward before going forward. In the honest version of the theory, all of them are in the sum. Every route that begins at the slit and ends at the chosen point, no matter how long or how ridiculous, each contributing its piece. Most of them, as we will see, contribute pieces that cancel against each other and leave no trace, which is exactly why the world does not look insane. But they are all in there. The photon is not choosing the least crazy option. It is doing all of it, and the sanity of the result is something the arrows produce, not something the photon assumed in advance. Now, your first objection is the right one, and it is worth saying out loud. If the photon takes every path, including the absurd ones that loop around the room, then why does light, in ordinary life, so obviously travel in a straight line? Why does a laser pointer make a straight beam? Why does the edge of a shadow look sharp? If light were really wandering down every possible route, the world should be a blur, and it plainly is not. This is exactly the right thing to worry about, and the answer to it is the most satisfying part of the whole idea. But we cannot get there yet, because first we need to understand what it means for a path to contribute, and how you add paths together. A path is not just a line on a map. Each path carries something with it, a little piece of quantum bookkeeping, and to add the paths up, we have to understand what that something is. Because if every path simply added its brightness to every other path, then more paths would always mean more light, and everything would be uniformly bright, and there would be no dark bands at all. The dark bands are the crucial clue. Somehow, adding more paths must sometimes produce less light, even nothing at all. Somehow the contributions from different paths must be able to cancel, to subtract, to erase each other. And a plain number, a plain amount of brightness, cannot do that, because brightness only ever adds. You need something that can point in different directions, something that can face one way for one path and the opposite way for another, so that when you combine them, they can either build up or cancel out. Feynman's genius was to give each path exactly such a thing. Not a number, but a little arrow, a tiny pointer with a direction that each path carries with it from A to B. And when you combine the paths, you do not simply add their sizes, you add their arrows, taking their directions into account. Arrows that point the same way reinforce. Arrows that point in opposite directions cancel. And with that one move, with the decision to attach a direction-carrying arrow to every path, the door opens to a pattern that has both brightness and darkness, both places where the light piles up and places where it disappears. So the question becomes, what sets the direction of the little arrow for each path? Why would one path's arrow point north and another's point south? The rule Feynman gave is simple, almost childishly simple, and it is where we turn next. Because once you see how each path winds its little arrow, the entire fringe pattern is only a matter of adding them up. Part 4. The Little Clock. Picture, on each and every path the photon might take, a tiny clock. Not a clock that tells the time of day, but a clock with a single hand, one arrow, spinning steadily around its face. This is Feynman's little arrow, and the image of a spinning clock is the one he used himself when he explained this to ordinary audiences, because it is exactly right and it hides nothing. Every possible path from A to B carries one of these little clocks, and the clock's hand is turning, around and around, at a steady rate, as the photon travels along that path. Here is the rule for the spinning. The hand of the clock turns at a fixed rate, set by the color of the light. Every color of light has a frequency, a rate of oscillation, and the little clock spins at that frequency. Red light has a lower frequency, so its clock spins a little slower. Blue light has a higher frequency, so its clock spins faster. For a given color, though, the rate is fixed and the same on every path. What differs from path to path is not how fast the clock spins, but how long it spins for. And that is the whole secret. Because a longer path takes more time to travel. If the photon is imagined moving along each path at the speed of light, then a path that swings wide and covers more distance takes longer than a path that goes nearly straight. And the longer the trip takes, the more times the little clock's hand goes around before the photon arrives at B. So when the photon reaches the end of a short path, its clock's hand has wound around to some particular angle, and when the photon reaches the end of a longer path, its clock has spun further, and its hand points in a different direction. Same spinning rate, different travel times, and therefore different final directions for the hand, path by path. That final direction of the hand, the way the clock's arrow is pointing at the moment the photon arrives at B, is the little arrow we talked about. That is the direction-carrying pointer that each path contributes. A path whose clock happens to finish with the hand pointing up gives you an up arrow. A path whose clock finishes with the hand pointing down gives you a down arrow. The clock is just the machinery that decides which way each path's arrow ends up facing, and the thing that decides it is simply how long the path is, translated into how far the hand had time to spin. Let me put you inside it for a moment, because this is one of those ideas that lives better in the body than in the abstract. Imagine shrinking down until you are the photon at the mouth of the slit. But you do not leave along one road. You leave along all of them at once, a whole spray of you, one version of you setting out on every possible path toward the far wall. And each version of you carries the same little clock, its hand spinning at the same steady rate, ticking as you travel. The version of you on the short, nearly straight road arrives quickly, and your clock has wound around only so far. The version of you on the road that swung wide arrives later, and that clock has spun further, its hand pointing somewhere else. When each version of you lands on the wall, you freeze your clock and hold up its hand, showing the direction it finished in. Thousands of versions of you, thousands of little clocks, each frozen at the angle its own journey earned. Not one traveler choosing a road, but a spray of travelers, each carrying the same patient spinning watch, arriving with their hands pointing every which way. Let me make the spinning rate concrete, because the color connection is more than a detail. It is the whole reason different colors of light behave differently. Visible light oscillates at a rate so fast it strains belief, something like hundreds of trillions of cycles every second, and each color sits at its own rate within that range. Red light, at the slow end of the visible band, has its clock turning at one pace. Violet light, at the fast end, has its clock turning nearly twice as fast, and the colors in between spin at their own steady rates in order. This is not a rate we chose for convenience. It is the actual frequency of the light, the same number that decides its color to your eye. So the little clock is not an invented gadget hovering over the physics. Its hand turns at the exact frequency of the light it belongs to, and that is why, later, the same construction will quietly explain why blue light bends and spreads by different amounts than red. The color you see and the speed the clock spins are one and the same fact. Hold on to how ordinary the ingredients are, because that is part of what makes the idea beautiful. There is no exotic machinery here, no hidden dimension, no mystical force. There is a travel time, which is just distance divided by speed, the same arithmetic you use to plan a car trip. There is a spinning rate, which is just the color of the light, and there is a final direction for a little arrow, which is just how far a steadily turning hand got in the time available. Anyone who can read a clock face and divide distance by speed already holds every piece. What makes it strange is not the parts but the instruction to apply them to every path at once, and then add the results. And it is that adding, that combining of all the little arrows into one, that we have to understand next, because it is where brightness and darkness are actually decided. Now, none of this means anything yet, because a single arrow, taken alone, tells you nothing about brightness. The whole point of attaching an arrow to each path is what happens when you bring the arrows together, when you take the clock hand from the straight path, and the clock hand from the wide path, and the clock hands from every path in between, and you combine them into a single answer. That combining step is where brightness and darkness are actually decided, where the spray of little clocks becomes a spot of light or a line of dark. But already you can feel the shape of the resolution to our earlier worry. If two paths have nearly the same length, their clocks spin for nearly the same time, and their hands finish pointing in nearly the same direction, and two arrows pointing the same way reinforce each other. But if two paths have very different lengths, their clocks finish pointing in very different directions, and arrows pointing in opposite directions fight each other and cancel. So whether a set of paths builds up brightness or cancels into darkness depends entirely on whether their little clocks finish in agreement or in conflict. And that, quietly, is where our sentence starts to earn its keep. Every path is taken, but only the ones whose clocks agree will survive the adding up. What we still have to do is learn exactly how to add these clock hands together and see what the adding reveals. Part 5. How you add the arrows. The way you combine the little clock hands is so simple that you could teach it to a child with a pencil. You take the first path's arrow and draw it. Then you take the second path's arrow, and instead of drawing it from the same starting point, you draw it starting from the tip of the first arrow. Then you take the third arrow and draw it starting from the tip of the second. And so on, arrow after arrow, each one beginning where the last one ended, laid down tip to tail like a chain of little pointers, each one pointing in whatever direction its own path's clock finished in. You are walking, step by step, each step in the direction that path's clock hand happened to point, each step the length of that arrow. When you have laid down every arrow from every path, one after another, you will have arrived somewhere. And now you draw one final arrow, the important one, straight from where you started the whole chain, the tail of the very first arrow, to where you ended up, the tip of the very last one. That final arrow, cutting across the whole winding chain from beginning to end, is called the resultant. It is the sum of all the little arrows, the single arrow that represents the combined contribution of every path at once. And here is the payoff, the rule that connects all of this abstract arrow drawing back to something you can measure on a wall. The probability that the photon actually lands at that point on the screen is proportional to the square of the length of the resultant arrow. Not the length itself, the length multiplied by itself. If the resultant is long, the photon is very likely to land there, and that spot is bright. If the resultant is short, the photon is unlikely to land there, and that spot is dim. And if the resultant has no length at all, if the chain of arrows wandered around and came right back to where it started, so that the beginning and the end are the same point, then the probability is 0, and that spot is perfectly dark. Let us feel what this rule can do, because it is more powerful than it looks. Suppose all the arrows in the chain happen to point in nearly the same direction. Then laying them tip to tail is like taking many steps all in the same direction, and you march a long way from your starting point. The resultant is long, its square is large, and the spot is bright. This is constructive combination, arrows in agreement, and it makes light. Now suppose the arrows point in wildly different directions, every which way, some up, some down, some left, some right. Then laying them tip to tail is like taking a drunken walk. One step this way, the next step that way, doubling back, veering off, and after all those steps, you end up not far from where you began, because the steps kept cancelling one another out. The chain curls around on itself, and the resultant, drawn from start to finish, is short. Its square is small, and the spot is dim. In the most extreme case, the chain of arrows curls all the way around into a closed loop, the last arrow's tip landing exactly on the first arrow's tail, and then the resultant has 0 length, and the spot is utterly dark. This is destructive combination, arrows in conflict, and it makes shadow. This is the machinery that lets adding more paths produce less light. It seems impossible on the face of it that adding another contribution could ever reduce the total, but with arrows it is easy. Add an arrow that points backward against the chain, and the resultant gets shorter, not longer. The darkness in our fringe pattern, those clean lines where no light lands, is not the absence of paths. It is the presence of many paths whose arrows, added up, curl around and cancel to nothing. The photon could have gone to that dark spot by countless routes, but the routes disagree so completely that, added together, they erase each other. Every path was taken. None survived the agreement. Let me show you the idea in miniature, with just a few paths, so the general behavior becomes visible. Imagine we take only 3 paths between A and B, and suppose that by chance their 3 clocks finish pointing in 3 different directions. We lay the 3 little arrows tip to tail, and we draw the resultant across them. It has some modest length, and its square gives us some modest probability. Fine. Now imagine 2 different situations. In the first, we choose 10 paths that all curve gently and are all close to the same length, so their 10 clocks all finish pointing in nearly the same direction. Laid tip to tail, those 10 arrows march almost straight, and the resultant is long. In the second situation, we choose 10 paths that curve wildly and differ greatly in length, so their 10 clocks finish pointing all over the place. Laid tip to tail, those 10 arrows stumble around in a rough circle, and the resultant is short, barely longer than a single arrow. The lesson jumps out. It is not the number of paths that decides whether a spot is bright. It is the agreement among their arrows. 10 paths whose clocks agree make a long resultant, and a bright spot. 10 paths whose clocks disagree make a short resultant and a dim one, even though there are exactly the same number of paths in both cases. Brightness is agreement, darkness is disagreement, and whether the arrows agree or disagree comes straight back to whether the paths have similar lengths, because similar lengths mean similar travel times, mean clocks that finish in similar directions. We now have, in principle, a complete recipe. To find how bright any point on the screen is, take every path from the slit to that point, spin each path's little clock according to how long that path is, lay all the resulting arrows tip to tail, draw the resultant, and square its length. Do that for every point on the screen, and you will have the entire brightness curve. It is a strange recipe, involving an unlimited number of imaginary journeys and a swarm of spinning clocks. But it is a real recipe, and it gives real numbers. Let me linger on the squaring step for a moment, because it is easy to skate past, and it is doing something important. Why square the length of the resultant, rather than just using the length itself? The honest answer is that this is the rule quantum mechanics hands us, tested against experiment for a century and never once caught being wrong. The arrow you build by summing is not itself the probability, it is a kind of intermediate quantity, and the probability of the event is the square of its length. The arrow can point in any direction, and its direction matters enormously while you are adding arrows together, because direction is what lets them reinforce or cancel. But once the summing is done, and you want an actual chance of the photon landing somewhere, the direction of the final resultant no longer matters, only its length, and you square that length to get the probability. So direction rules the middle of the calculation and vanishes from the end of it. This is why two spots with resultants of the same length are equally bright, regardless of which way their final arrows happen to point. And it is why a spot can be dark, not because no arrows reached it, but because the arrows that reached it summed to a resultant of zero length. There is a small, satisfying consequence worth naming. Because we square the resultant, doubling the length of the resultant does not double the brightness, it quadruples it, and halving the resultant does not halve the brightness, it quarters it. Brightness responds steeply to how well the arrows agree. A modest improvement in agreement, a resultant a little longer, produces a disproportionately brighter spot, and a modest breakdown in agreement produces a disproportionately darker one. This steepness is part of why the fringe pattern has such crisp, well-defined bands rather than a gentle wash, why the bright fringes are so bright and the dark fringes so definite. The squaring sharpens the contrast, taking the smooth swelling and shrinking of the resultant and turning it into vivid stripes. But it also looks, right now, like an impossible amount of work. And worse, it looks like it should give nonsense, because we still have not answered the nagging objection. If the photon really takes every path, including the crazy ones that loop around the room, then those crazy paths have their arrows in the chain too, and it seems like the whole thing should dissolve into noise. Why does anything clean and sharp survive at all? Why does light, in the end, behave as though it went nearly straight? To answer that, we have to look closely at what the crazy paths actually do when you add them, and the answer is the quiet turning point of this entire story. Part 6. Why the straight path wins. Take the wildest paths first, the ones your intuition wants to throw out, and watch what happens to them when you add their arrows. Consider a whole family of paths that swing far away from the straight line, looping and curving all over the space between A and B. Because they wander so differently, their lengths are all over the place. One of them is a little longer, the next much longer, the next longer still, each one covering a wildly different distance. And since the length of a path decides how long its clock spins, these wandering paths have clocks that finish pointing in completely different directions, one at this angle, the next at a totally different angle, with no relationship between neighbors. When you lay their arrows tip to tail, you get that drunken, stumbling walk, arrows lurching in every direction, the chain curling back on itself. The resultant across such a family of wild paths is tiny. They cancel each other almost perfectly. For every wandering path pushing the chain one way, there is another wandering path, only slightly different, whose clock finished pointing nearly the opposite way, shoving it back. Added up, the wild paths contribute almost nothing. Now consider the paths that stay close to the straight line, the nearly direct routes. Here, something completely different happens. Because these paths are all close to straight, their lengths are all very nearly the same. And here is the subtle, crucial point. Near the straightest path, changing the path a little barely changes its length at all. Think about it. If you take the shortest route between 2 points and nudge it slightly to one side, the new route is only a hair longer, because near the minimum, small changes in the path produce only tiny changes in length. So all the nearly straight paths have almost identical lengths, which means their clocks spin for almost identical times, which means their little arrows all finish pointing in almost the same direction, and arrows pointing the same direction, laid tip to tail, march in a nearly straight line, building a long resultant. The nearly straight paths reinforce each other. They agree. So when you add up every path, wild and straight alike, the wild ones cancel themselves into insignificance, and the nearly straight ones pile up into a strong resultant. The final answer is dominated, overwhelmingly, by the small bundle of paths clustered around the straight line. It is not that the photon was forbidden from taking the wild paths. It took them all. It is that the wild paths, added together, erased themselves, while the straight ones survived. And the effect only gets sharper the more paths you include. Add more and more wandering paths, and they cancel more and more completely, while the near straight bundle keeps standing. Counterintuitively, considering more paths does not smear the answer into mush. It sharpens it, because the extra paths are almost all cancellers. There is our answer to the objection that has been following us since the beginning. Light appears to travel in a straight line, in ordinary life, not because it is forbidden from wandering, but because all its wanderings cancel out, and only the straight bundle is left standing. The sharp edge of a shadow, the clean beam of a laser pointer, the straight shaft of sunlight through a gap, all of it is the residue of a colossal cancellation. Underneath the tidy straight line, the light is going everywhere, and everywhere is quietly deleting itself, except along the route we call straight. This is what lets us, from here on, keep only the nearly straight paths in our calculations, and throw the wild ones away, not because they do not exist, but because we already know they add up to nothing. Keeping the straight line paths is not a cheat. It is us doing, on paper, what the arrows already did on their own. I want to stop here, because this is the moment where a piece of the world quietly changes shape, and it deserves a breath. The straight line has always felt to you like the obvious path, the real path, the one the light truly takes. Every instinct you have about motion is built on the idea that a thing goes from here to there along one definite route, the sensible one, the direct one. And what Feynman's arrows are telling you is that nature does not work that way underneath. Nature does not select the sensible route in advance and send the photon down it. Nature takes every route, all of them, the sensible and the absurd, together, and then lets them interfere. The straight line is not chosen. It is what is left over when everything else cancels out. The orderly, single-track path you believed in is not the truth beneath the pattern. It is the survivor of an unimaginable everywhere, the one bundle of journeys that happened not to erase itself. The photon did not walk a line to the wall. It explored the entire space between, and the line is only where the exploration failed to cancel. Let that settle, because it does not stay politely inside the physics of light. It is a statement about how the definite, reliable, single-track world you live in might be assembled, underneath, out of an unthinkable multiplicity that mostly deletes itself before you ever see it. The calm straight beam is a kind of illusion of simplicity, and the simplicity is not a lie exactly, but it is a leftover, a residue, the thin surviving trace of a sum over everything. Think about what your certainty in the straight line was really built on. It was built on watching things at human scale, where the cancellation is so complete that you never once caught nature in the act of taking the other paths. Every ball you ever threw, every stone that ever fell, every beam of light you ever followed with your eye, arrived exactly where the single straight or curved classical path said it would, with no visible hint of the countless other routes. And from that lifetime of evidence you drew the reasonable conclusion that the classical path is simply what happens, the one real motion. You were not being foolish. You were reading the surface of the world accurately. It is only that the surface is the residue, and the residue is so clean, so sharp, so free of the cancelled wanderings, that it looks like the whole story, rather than the leftover of a much larger one. Your intuition was not wrong about what it saw. It was wrong only about what lay underneath what it saw. And this is the quiet reason the slit experiment matters so much. Out of all the ways one could demonstrate quantum behavior, it is a place where the cancellation is not quite complete, where the surviving bundle of paths is wide enough that its edges show. The slit is narrow enough, the light delicate enough, that the wandering paths do not perfectly erase, and what leaks through is the banded pattern, the visible fingerprint of all the paths that almost cancelled, but not quite. You are not looking at some special exotic light that behaves differently from ordinary light. You are looking at ordinary light in a situation contrived so that the everywhere, normally hidden beneath a flawless residue, is allowed to leave a mark you can photograph. The wall of bright and dark bands is the sum over all paths, caught in the one place it forgot to hide. We now understand, in pictures, why the pattern forms, and why straight-line behavior emerges from a sum over all paths. But pictures can only take us so far, and Feynman did not stop at pictures. He turned this into real mathematics, a short and honest calculation that takes the spinning clocks and produces, on paper, the exact brightness curve we measured, tall central peak and shrinking hills and all. And before we do that arithmetic, we should return to the slit itself and watch the arrows build the actual fringe pattern, point by point across the screen, so that when the equations arrive, we already know in our bones what they are going to say. Part 7. Watching the pattern assemble itself. Let us go back to the slit and do the whole thing properly, point by point across the screen, and watch the fringe pattern draw itself out of nothing but spinning clocks. We keep only the nearly straight paths now, because we have earned the right to. So picture the slit, a narrow opening, and picture straight-line paths leaving from every point across the width of that opening, from the very top edge, from the middle, from the bottom edge, and from everywhere in between, all heading toward one chosen point on the screen. For simplicity, imagine we track just 10 of these paths, 10 straight lines spanning the slit, all aimed at the same landing spot. Each of those 10 paths has a slightly different length, because each one starts from a slightly different height within the slit, and so each one's little clock finishes pointing in a slightly different direction. 10 paths, 10 clocks, 10 arrows. Now let us choose our landing spot to be dead center on the screen, straight ahead of the slit. Think about the 10 path lengths for that central point. Because the center is directly opposite the slit, the 10 paths from across the slit to that central point are all very nearly the same length as one another. The path from the top of the slit and the path from the bottom of the slit reach the center by journeys that differ only slightly. Similar lengths mean similar clock times, mean arrows that all finish pointing in nearly the same direction. We lay those 10 nearly aligned arrows tip to tail, and they march almost straight, and the resultant is long. Squared, it gives a high probability. The center of the screen is bright. There is our central band. Now let us slide our chosen landing spot away from the center, out toward the side. Watch what happens to the 10 path lengths. As the target point moves off to the side, the path from the near edge of the slit gets shorter, and the path from the far edge gets longer, and the spread of path lengths across the slit grows. A wider spread of lengths means a wider spread of clock times, which means the 10 arrows now finish pointing in a fan of different directions instead of all together. We lay them tip to tail, and the chain begins to curl, and the resultant, drawn across the curl, is shorter than it was at the center. The spot is dimmer. Slide a little further out, and the fan of directions grows wider still. The chain curls more tightly, and the resultant shrinks further. Keep sliding, and you reach a very particular place where something clean happens. At a certain distance from the center, the spread of path lengths is just right, so that the 10 arrows fan out through a full turn, and the chain of arrows curls all the way around into a closed loop, the tip of the last arrow meeting the tail of the first. When that happens, the resultant has 0 length, because you ended exactly where you began. The probability is 0. The light vanishes completely. That is the first dark band, and it was made not by an absence of paths, but by 10 arrows curling into a perfect circle and cancelling themselves to nothing. Slide past that dark band, and the arrows begin to come back into partial agreement, the chain opening up again, the resultant growing back to some modest length, and you get a smaller, dimmer, bright band. Slide further, and the arrows wrap around even more than a full turn, curling into a loop and a bit, and the resultant collapses again, giving another dark band. And so it goes, outward across the screen, the resultant swelling and shrinking, as the arrows drift into and out of agreement, painting bright band, dark band, dimmer bright band, dark band, exactly the fringe pattern we set out to explain. Let me put you at the screen for this, because it is worth seeing with your own imagined eyes. Stand at the wall where the light lands, and let yourself slide slowly sideways, and at each step watch the little arrows for the paths that reach the very spot where you are standing. When you are at the center, the arrows all point nearly the same way, and when you chain them, tip to tail, they stretch out into a long, straight run, and the light piles up around you. Brilliant. Now walk slowly outward. The arrows begin to disagree, just slightly at first, and the chain starts to bend, like the tip of a fern curling. Keep walking, and the bend tightens, the chain coiling in on itself, and the light around you fades. Take one more step, and the coil closes into a perfect circle, tip touching tail, and the light where you stand simply switches off, a band of pure dark, made by arrows that ate themselves. Walk on, and a smaller coil opens, and a dimmer light returns. The whole banded pattern is not painted on the wall in advance. It is being drawn, live, by the turning of clocks, and you are walking through the places where they agree and the places where they war. And now recall the little detail I asked you to hold on to at the very beginning, the one about the central band being twice as wide as the others. Watch it appear here, for free. Starting from the center and sliding outward, you have to travel a certain distance before the arrows first wrap all the way around and give you that first dark band. But once you are past it, each successive dark band comes after the arrows wrap around just one more time, and that takes only half as much sliding as the first wrap did, because getting the arrows to go from no wrapping to one full wrap covers more screen than getting them from one wrap to two. So the central bright region, which stretches out to that first dark band on either side, is twice as wide as each of the side bands squeezed between later dark bands. The 2-to-1 ratio you noticed idly at the start was not a coincidence of that particular laser. It was the arrows all along, and we are watching it be born. There is a subtlety in the fading of the side bands that the arrows also explain, and it is worth a moment because it deepens the picture. You might expect that once you are past the central bright region, the side bands would all be roughly equal, like a row of similar hills. But they are not. Each successive side band is noticeably dimmer than the one before it. fading steadily as you move outward. The arrows tell you why. At the first sideband, past the first dark loop, the chain of arrows has wrapped around once, and then a little more, so that most of the arrows cancel in the closed loop, and only a small leftover arc sticks out to form a short resultant. At the next sideband, the chain has wrapped around twice and a little more, so an even larger fraction of the arrows is consumed in the closed loops, and an even smaller leftover forms the resultant. The further out you go, the more of the arrows are swallowed by complete cancellation, and the less is left over to make light. So the sidebands do not just exist, they fade in a specific, calculable way, each one built from the crumbs left after more and more complete cancellation. The pattern is not a row of equal stripes, it is a tall central spike, followed by a decaying series of ever fainter ghosts of it, and every feature of that decay is written in how the arrows curl. Step back and notice what we have actually accomplished standing here at the wall. We began with a claim that sounded like a provocation, that a photon takes every path, and we have used it, with nothing more than the rule that each path carries a spinning clock, and the rule that you add the clock hands tip to tail and square the resultant, to reconstruct by hand the entire shape of a real diffraction pattern. Not just that it has bright and dark bands, but where the first dark band falls, why the central band is double width, and why the side bands fade as they go. Every qualitative feature a physicist would list about single-slit diffraction has fallen out of the arrows, in pictures, before we have written down a single equation. That is already remarkable. But physics is not satisfied with qualitative agreement, because many wrong ideas can produce roughly the right shape. The test is whether the exact curve matches, number for number, and for that we finally have to translate the arrows into arithmetic. This is already a small triumph. Using nothing but rotating arrows and the rule that you square the resultant, we have reconstructed, qualitatively, the entire single-slit fringe pattern, the bright center, the dark bands, the fading side bands, and even the width ratio, out of an idea that sounded, an hour ago, like a provocation. But qualitatively is not the same as exactly, and physics lives or dies on exactly. So the question now is whether this arrow picture, turned into honest mathematics, spits out the precise brightness curve, the one with the specific shape a light meter measures. And it does. The calculation is shorter than you might fear, and every step in it is something we have already seen in pictures. So let us do it. Part 8. The honest arithmetic. We are going to turn the spinning clocks into equations now, and I promise to keep every step tied to a picture you have already seen, so the mathematics never floats free of meaning. Start by setting up the geometry. Put the slit upright, centered on a line running straight ahead to the screen. Call the width of the slit A, so the top edge of the slit sits at a height of half of A above the center, and the bottom edge sits at half of A below it. Put the screen a distance L away, straight ahead. Now pick a point on the screen and measure how far it is from the center of the screen. Call that distance X. Our job is to find the length of a straight path that leaves the slit at some height, call that height Y, and lands at the point X on the screen. That path is the slanted side of a right triangle. One side of the triangle runs straight from the slit to the screen, the distance L. The other side runs along the screen, and its length is the difference between where the path lands, X, and where it started in the slit, Y. So that side has length X minus Y. The path itself is the long slanted side, the one connecting start to finish. And by the theorem of Pythagoras that you learned in school, its length squared equals L squared plus the quantity X minus Y squared. That is the exact path length. It is a little awkward with that square root lurking in it, so we tidy it up, using a fact about our actual setup. The fact is that the screen is far away compared to how narrow the slit is and how small the pattern is. In the real experiment, the distance L might be several meters, while the slit is a fraction of a millimeter, so the sideways distances are tiny next to L. When a quantity is tiny compared to another, there is a standard and honest approximation that lets you unpack a square root into something simpler, and applying it here turns the awkward path length into something clean. The path length is approximately L plus the quantity x minus y squared divided by twice L. That is the length of the path from height y in the slit to point x on the screen, near enough to exact for anything we will ever measure. Now translate length into clock spinning. The clock spins at a rate set by the light's frequency, and it spins for as long as the photon travels, which is the path length divided by the speed of light. So the total angle the clock hand turns through for a given path is the spinning rate multiplied by the travel time. Feed in the path length we just found, and the total angle has two pieces. One piece comes from the L part of the length, and one piece comes from the x minus y part. Here is a clean simplification we have actually already reasoned out in pictures. The first piece, the one from the L part of the length, is exactly the same for every single path to a given point on the screen, because every path shares that same L. A rotation that is identical for every arrow does not change how the arrows differ from one another. It just turns the whole chain rigidly, like rotating a drawing without changing its shape. And since only the differences between arrows decide whether they agree or cancel, we can ignore that common piece entirely. What is left is the piece that actually varies from path to path, the piece built from x minus y, and that is the piece that carries all the pattern. To write that surviving piece compactly, physicists use a number called the wave number, written k, which is just a convenient way of packaging the light's color. It equals 2 times pi divided by the wavelength, and a shorter wavelength means a larger k. In terms of k, the path-dependent angle of the arrow works out to k times the quantity x minus y squared divided by twice L. Expand out that square and you get 3 terms. One term depends only on x, not on y, so like before, it is the same for every path to the point x, and we can drop it. Another term turns out to be so small for realistic numbers that it can be neglected too. If you plug in a red laser of about 650 billionths of a meter, a slit about 50 millionths of a meter wide, and a screen about 5 meters away, that term comes to about 6/100ths, which is tiny compared to 1, so it changes nothing. And when the dust settles, the angle of the little arrow for a path leaving height y and landing at x reduces to a single, clean expression. It is proportional to minus k times x times y divided by L. Now watch the little clock reveal its true identity, because this is where the childlike image and the serious mathematics turn out to be the same thing. A spinning arrow of fixed length, pointing at some angle, is exactly what mathematicians describe with one of the most quietly beautiful results in the subject, a relationship discovered by Euler. It says that an arrow of length 1, pointing at an angle, can be written as a single compact expression built from that angle. The physicists call it a complex exponential, but you do not need the name. You need only the meaning, which is this. It is the mathematics of a unit arrow pointing in a direction. Our little clock hand, spinning around its face, is precisely this object. The homely spinning watch and the elegant formula from Euler are not two things. They are one thing, seen from two sides. So each path contributes one of these unit arrows, pointing at the angle we just found, minus k times x times y over L. And summing over all the paths across the slit means adding up all these arrows as y sweeps continuously from the bottom edge of the slit to the top edge, from minus half of a to plus half of a. Adding up a continuous sweep of arrows is exactly what the mathematical operation called integration does. An integral is nothing more mysterious than a tip-to-tail sum of infinitely many infinitesimal arrows. We carry out that sum across the slit, and the answer comes out in terms of a function that appears all over physics, the function that takes an angle and gives the sine of that angle divided by the angle itself. Written out, the length of the resultant arrow at point x is proportional to the slit width a, multiplied by this function of a times k times x, divided by twice l. That resultant is the summed arrow, the long or short pointer whose square tells us the brightness. So to get the actual brightness, we do the final step our rule always demanded. We square it. And squaring gives the probability of the photon landing at x, proportional to a squared, times the square of that same function of a times k times x over twice l. And now comes the moment the whole exercise was for. If you plot that expression against x, position across the screen, you get a tall central peak, dropping to 0, rising to a much smaller side bump, dropping to 0, rising to a smaller bump still, on and on outward. It is the exact curve a light meter traces across a real single-slit pattern. Not approximately, exactly. Starting from the outrageous premise that the photon takes every path, carrying a little clock, we have arrived, in a page of honest arithmetic, at the precise brightness curve of classical wave optics, the one physicists measured and knew long before anyone spoke of photons taking every road. Take a moment to feel the size of that. The strangeness of light taking every path is not a story we tell around the data to make it exciting. It is the data. The spinning clocks are not a metaphor bolted onto the pattern afterward. They are the thing that produces the pattern. And the proof is that when you take them literally and do the arithmetic, the numbers land exactly where the light lands. I want to dwell on one moment in that calculation, the moment Euler's formula appeared, because it is the quiet hinge of the whole thing, and it deserves to be felt rather than rushed. For most of this journey, the little clock has been a friendly cartoon, a watch face with a spinning hand, the kind of thing you would draw for a child. It was easy to picture and easy to trust, but you might have wondered, in the back of your mind, whether it was only a picture, a helpful story, that a real physicist would replace with something colder and more serious. And then, in the arithmetic, when we needed to write down a unit arrow pointing at an angle, the object that appeared was exactly Euler's expression, one of the most celebrated results in all of mathematics, the formula that ties together a turning angle and the notion of an exponential. The cartoon clock and the serious formula turned out to be the same thing, wearing different clothes. Feynman's little spinning hand is not a simplification of the real mathematics. It is the real mathematics, drawn honestly. The friendly picture and the professional equation are one object, and that is why the picture never lied to us. There was nothing underneath it to hide. There is also a lesson in how much we were able to throw away and still get the exact answer, and it says something about how physics actually works. We dropped a whole term because it was the same for every path. We dropped a second term because, for realistic numbers, it came out to about 6/100ths, small enough to ignore. This is not sloppiness. It is the craft of the subject, the art of seeing which parts of a calculation carry the meaning and which parts are along for the ride. The terms we discarded were not errors, they were simply features that either did not vary between paths and so could not affect the pattern, or were so tiny under real conditions that including them would change the answer by less than any instrument could measure. Learning which terms matter is most of what it means to understand a piece of physics. And here, the arrows guided us, because they told us in advance that only the differences between paths could carry the pattern. So any piece that was common to all paths could be set aside without a second thought. And once you have this machine in your hands, you can start turning its knobs and asking what happens, and the first knob to turn is the width of the slit itself. Part 9. Squeeze the light, and it spreads. There is something almost perverse about what happens when you make the slit narrower. and the arrows explain it perfectly. Your intuition says that if you want a narrower, tighter beam of light on the far wall, you should use a narrower slit. Squeeze the opening down, and surely the light is forced into a thinner channel and lands in a thinner strip. That is what would happen with a stream of sand, or a spray of pebbles, or anything that behaves like a simple hail of particles marching straight ahead. Narrow the gate, narrow the stream. But light, built out of a sum over paths, does the opposite. Make the slit narrower, and the pattern on the screen spreads out wider. Squeeze the light in space, and it fans out more, not less. Open the slit up wide, and the pattern tightens into a sharp, bright line. The tighter you pinch, the broader it blooms. Let us see why, using the picture we have already built, because it falls right out of the arrows. Recall that a dark band appears at the place on the screen where the chain of little arrows curls all the way around into a closed loop and cancels to nothing. That closing of the loop depends on the spread of path lengths across the slit, which is to say, on the difference in how far the clock at the top edge of the slit has to spin compared to the clock at the bottom edge. When those two edge clocks differ by exactly one full turn, the arrows in between fan out through a complete circle, the chain closes, and you get the first dark band. Now ask what the slit width does to that. If the slit is wide, then the top and bottom edges are far apart, and even for a landing point, only a little off-center, the path from the top edge and the path from the bottom edge already differ substantially in length, so their clocks already differ by a full turn close to the center. The first dark band arrives quickly, near the middle, and the whole pattern is squeezed into a narrow central region. But if the slit is narrow, then the top and bottom edges are close together, and the two edge paths stay nearly equal in length until the landing point has moved far out to the side. You have to go a long way from center before the edge clocks finally differ by a full turn and close the loop. The first dark band arrives far out, and the central bright region is stretched wide. Narrow slit, distant first dark band, broad pattern. It is the arrows, doing exactly what they must. And this is one of those places where the mathematics we built pays a clean dividend, because it tells us not just that the pattern spreads, but exactly how much. The condition for that first dark band is that the clock at one edge of the slit and the clock at the other differ by one full turn. And if you write that condition out using the expressions we found and solve it for the position of the first dark band on the screen, you get something beautifully simple. The distance from the center to the first dark band equals the wavelength of the light, multiplied by the distance to the screen, divided by the width of the slit. That is the whole rule. The location of the first dark fringe is wavelength times screen distance, divided by slit width. Read that little formula slowly, because everything we just said in words is sitting right there in it. The slit width is on the bottom, in the denominator. So when the slit width shrinks, the distance to the first dark band grows, and the pattern spreads. When the slit width grows, the distance to the first dark band shrinks, and the pattern tightens. The equation and the arrows and the intuition all agree, and they agree quantitatively. Put in real numbers. A red laser, around 650 billionths of a meter. A slit 50 millionths of a meter across. A screen 5 meters away. And the formula tells you the first dark band sits about 6.5 centimeters out from the center. A hand's width of spreading from a slit you can barely see. And this same formula quietly contains the 2-to-1 width ratio we keep returning to, because the central band runs from the first dark band on one side to the first dark band on the other, spanning twice that distance, while each sideband is squeezed into a single such distance. The detail you noticed at the very beginning, the central fringe being twice as wide as its neighbors, is written directly into this one small equation. Consider how much this single formula quietly ties together. The wavelength sits on top, so redder light with its longer wavelength, spreads more than bluer light through the same slit, which is why, when white light passes through a fine opening, the colors fan out by different amounts and separate. The screen distance sits on top too, so the further away you put the wall, the wider the pattern grows, spreading in simple proportion to the distance, which is why diffraction, that is invisible up close, becomes obvious across a room. And the slit width sits underneath, delivering the counterintuitive spreading we started with. 3 everyday quantities, a color, a distance, and a width, combined in the plainest possible way, and out comes the exact location of the darkness. There is something almost startling in how ordinary the ingredients are, and how strange the result, and it is a small monument to how far we have come, that a formula this simple now feels not like a rule handed down from a textbook, but like something we earned, arrow by arrow, from the idea that the light went everywhere. It is worth appreciating that this same spreading is not a nuisance confined to physics demonstrations. It sets hard limits on what any eye or instrument can ever see, because light spreads when it passes through any opening, every lens, every telescope, every microscope, every camera, and the pupil of your own eye has a fundamental blurring built into it, a smallest possible spot to which it can focus light, set by exactly this diffraction. A larger opening spreads the light less, and so can resolve finer detail, which is one basic reason astronomers build ever larger telescopes, not only to gather more light, but to beat down the diffraction spreading and see sharper. The very effect, making bands on our wall, is the effect deciding how clearly humanity can photograph a distant galaxy or a living cell. What looks like a curiosity in a dark room is a law that reaches all the way out to the edge of the observable, and all the way in to the smallest thing a lens can show you, and it all traces back to the arrows fanning out from a narrow gap. There is one more piece the arrows insist on, and it is about brightness, not just width. When you narrow the slit and spread the pattern out, you are also gathering light from fewer paths, because a narrower slit simply has less room in it for paths to leave from. Fewer paths means a shorter resultant arrow even at the bright center, and since brightness is the square of the resultant, the whole pattern also gets dimmer as it spreads. The mathematics says the peak brightness falls off with the square of the slit width. So halving the slit does not just double the spread, it quarters the peak brightness. Squeeze the light, and it spreads wider and fainter at once, painting a broad, dim smear instead of a narrow, brilliant line. I want to name what this really is, because you have met its cousin before, even if you have never seen this experiment. This trade, where confining light more tightly in space forces it to spread more widely in direction, is the same trade that lies at the heart of the uncertainty principle, the famous statement that you cannot pin down certain pairs of quantities at once. Here it is, in its most visible, most physical form. Pin the light down tightly in position by forcing it through a narrow slit, and it responds by becoming wildly uncertain in direction, fanning out across the screen. Let it stay loose in position by using a wide slit, and it becomes sharp in direction, holding a tight line. The slit experiment is not merely similar to the uncertainty principle, it is the uncertainty principle, made out of nothing but path lengths and spinning clocks, laid out on a wall where you can measure it with a ruler. The strangeness we have been building toward is not confined to equations. It is the same strangeness that governs everything small, and here it is, casting bands of light and dark you can photograph. So we have taken our machine and turned its first knob, the width of the slit, and it told us something both counterintuitive and exact, and it connected our humble laser to one of the deepest principles in physics. Now let us turn a more dramatic knob. Let us cut a second slit beside the first, and ask what a single photon does when it is offered not one opening, but two. Because it is here, with two slits, that the idea of light traveling everywhere at once stops being a way of speaking and becomes something you can very nearly watch. Part 10. Through both. Cut a second slit beside the first, two narrow openings side by side, and shine the light through, and the pattern on the screen changes in a way that has unsettled physicists for 200 years. With two slits, the bands on the screen become finer and more numerous, a whole comb of closely spaced bright and dark fringes, and this time the bright fringes are all about the same width, rather than having a double wide one in the middle. If you scan a light meter across it, you find these fine, evenly spaced fringes sitting underneath a broader, gentler swell of brightness, as if a fine picket fence of light and dark had been drawn on top of a soft, wide hill. Two patterns, one nested inside the other, and our task is to show that the sum over paths idea, the same little clocks, produces exactly this, and in doing so, makes the phrase everywhere at once almost literal. The recipe barely changes. Before, we summed the arrows from all the paths leaving one slit. Now we simply sum the arrows from all the paths leaving both slits. For any chosen point on the screen, we find the resultant arrow from all the paths through the first slit, then find the resultant arrow from all the paths through the second slit, and then add those two resultants together, tip to tail, to get the grand resultant for both slits. Square its length, and that is the brightness at that point. That is the entire change. Two families of paths instead of one, their resultants combined. And when you carry that through, the answer splits cleanly into two effects multiplied together. One factor is exactly the single slit pattern we already derived, the broad hill with its tall center and shrinking sides, coming from the paths spreading out within each individual slit. That is the soft, wide swell. The other factor is a new, rapidly rising and falling term that comes from the interference between the two slits, from whether the resultant arrow of the first slit agrees or disagrees with the resultant arrow of the second. That is the fine picket fence of closely spaced fringes. The final pattern is the single slit hill, acting as an envelope, a gentle outline with the two slit fringes drawn finely inside it. The mathematics hands you both at once, the envelope and the comb, precisely matching what the light meter measures. Now, all of that is bookkeeping, and it is correct, and it reproduces the data. But I have been holding something back, the thing that makes the two-slit version, the one that keeps physicists up at night, and it is this. Remember that we can turn the light down until only a single photon crosses the apparatus at a time, alone, with nothing else in flight. Do that with two slits. Send the photons one at a time, minutes apart if you like, each one utterly by itself, and record where each lands. As before, the individual dots seem random, and as before, the dots slowly pile up into a pattern. But the pattern they pile up into is the two-slit interference pattern, the fine comb of fringes, complete with dark lines, where almost no photon ever lands. Sit with what that requires. A single photon, alone in the apparatus, ends up building a pattern that depends on there being two slits. If the photon had simply gone through the left slit, it should not care whether the right slit is open. If it had simply gone through the right slit, it should not care about the left. But the pattern it helps build is a two-slit pattern, a pattern of interference between the two openings, and interference between two openings only makes sense if something went through both. A lone photon, indivisible, produces a result that depends on both slits at once. In the language of the arrows, the resultant it contributes to is the sum of paths through the left slit and paths through the right slit together. The photon did not pick a slit, it went through both as two families of roads and interfered with itself. Let me put you inside this one, because it is the heart of the whole video, the place the title finally comes true. You are the photon again, released alone, drifting toward the barrier with its two openings. You do not choose. You go through both, splitting into two families of roads, one family fanning out from the left slit, one from the right, each road carrying its own little clock, spinning. On the far wall, the two families arrive and their arrows are laid together and summed. and wherever the combined chain is long, the wall is allowed to be bright, and wherever it curls up and cancels, the wall is forbidden, dark. And the thing I need you to feel is the aloneness of it. There is no other photon anywhere in the room. There is nothing for you to interfere with, except the other versions of your own journey, the you that went left, and the you that went right meeting again on the wall. Through both is not a figure of speech now. It is the plain description of what one grain of light does when nobody is watching which way it went. This is the moment to stop pretending it is only about lasers and walls, because it is about the light falling on you right now. The realization is this: they can send the photons one at a time, each one completely alone, and the interference pattern still assembles itself, which is only possible if, in some real sense, each single photon went every way at once. A single indivisible speck of light interferes with itself. And this is not a rare event coaxed out of an exotic machine in a distant laboratory. It is what light does. It is the nature of the light coming off this screen or this page into your eyes at this very moment. The everywhere at once is not a special effect reserved for physicists. It is ordinary. It is happening in the light around you, all the time, everywhere, and it is only the scale and the speed of it that keep the sum hidden from your eyes. The strangeness we have been building toward is not out there. It is here, in the room, in the light on your hands. There is a temptation, when you first meet this, to try to catch the photon in the act, to set up a little detector at each slit and simply watch which one the photon goes through and settle the matter. And people have done exactly that, and the result is its own quiet lesson. The moment you install a detector that genuinely determines which slit each photon passes, the interference pattern vanishes. The fine comb of fringes disappears, and what you get instead is the plain two-stripe pattern you would expect from little bullets, one pile behind each slit. As soon as you force the photon to commit to a single slit, to make one of its two families of paths into a fact and the other into a non-event, you have destroyed the very thing that made the fringes, because the fringes were the interference between both families, and you have just erased one of them. Look to see which way it went, and it went one way, and the everywhere collapses. Stop looking, and it goes both ways again, and the everywhere returns. We will not chase all the way down that particular corridor tonight, because it opens onto the deepest and most argued questions in the subject. But it is worth knowing that the everywhere is not merely hard to see. It is something that hides itself the instant you pin it down. Hold that beside the aloneness of the single photon, and let the two facts press on each other. On one hand, a lone photon, with nothing to interfere with, builds a pattern that requires it to have gone through both slits. On the other hand, the instant you check which slit, it turns out to have gone through only one, and the pattern dies. The photon behaves as though it took every route right up until the moment the world extracts a definite answer about where it was, and then it behaves as though it took one. This is not a contradiction the arrows resolve for you. It is the texture of quantum reality itself, the thing that no comfortable picture fully tames. What the arrows do give you is the ability to compute exactly what the pattern will look like in either case, whether you look or you do not. And that is the strange bargain at the heart of this physics. It tells you with perfect precision what will happen, while leaving you to sit, a little unsettled, with what it means. For 2 centuries this was described with a kind of helpless wonder, a paradox to be marveled at and not explained. What Feynman's arrows give you is not a way to make the wonder go away, but a way to make it precise. The photon goes through both slits because it goes through everything. It takes every path, and the 2-slit pattern is simply what survives when the arrows from every path through both openings are added up. The mystery is not dissolved. It is given a shape and a set of numbers, and those numbers are correct. And once you accept that this is how a photon behaves, a natural and slightly vertiginous question arrives. Is this only true of light? Or is everything you are made of, playing the same game underneath. Part 11. Not just light. The most quietly shocking thing about everything we have built is that none of it is really about light. We have been talking about photons, about a red laser and a slit and a wall, because light is where the pattern is easiest to see. But nothing in Feynman's construction actually required the traveler to be a photon. The rule was simply this: take a particle that starts here and ends there. Give every possible path between them a little spinning clock. Add up the arrows and square the resultant to get the probability. Nowhere in that recipe did we use any special property of light, and that means the same recipe should apply to anything that behaves quantum mechanically, which is to say, to everything. So take an electron, a particle with mass, a piece of ordinary matter, the very stuff your body is built from. Fire electrons, one at a time, at a barrier with 2 slits, and record where each lands on a detector behind it. Your intuition screams that an electron is a little bit of matter, a tiny bullet, and a bullet goes through one slit or the other and lands in one of 2 piles. But that is not what happens. The electrons build up, one lonely dot at a time, into an interference pattern, the same comb of bright and dark fringes we saw with light. A single electron, alone, passes through both slits and interferes with itself, exactly as a photon does. This has been done in the laboratory, carefully, electron by electron, and photographed as the pattern slowly emerges from what looks at first like random scatter. Matter travels everywhere at once, just as light does. Pause on how radical that is, because we have grown so used to hearing it that it can slide by. An electron is not a convenient abstraction. It is a genuine constituent of you, one of the particles whose behavior determines the chemistry of every cell in your body. If an electron takes every path, then the matter you are made of is playing the same game as the light in the room, exploring all its routes and letting the arrows decide. The reason you do not feel yourself smeared across possibilities is the same reason a thrown ball flies in a clean arc, and we are moments away from that reason, but the raw fact deserves to land first. The wave nature is not something that happens only to light, or only to things that seem ghostly and immaterial. It happens to solid matter, to the stuff of tables and hands and planets, all the way up in principle, and it has been demonstrated in the laboratory up to objects you could almost think of as tiny grains. The line you imagined between the strange quantum world and the solid ordinary one does not exist as a line. There is only one world, and it is quantum all the way through. And there is a beautiful unifying quantity hiding inside the fact that both light and matter diffract, a bridge between them worth naming. Every particle of matter, an electron, a neutron, an atom, has associated with it a wavelength, a length that plays the same role its color wavelength plays for light, and it is set by how fast and how heavy the particle is. The faster and heavier the object, the shorter its wavelength. This is why a thrown ball shows no visible diffraction. Its wavelength is so unimaginably tiny, far smaller than an atom, that no slit could ever be narrow enough to spread it. And it is why an electron, light and slow, has a wavelength large enough to diffract through a suitably fine grating, and why the 60-atom molecules, heavier still, needed an even finer arrangement to reveal theirs. The same formula we found for light, the spreading set by wavelength over slit width, governs matter too, once you know the matter's wavelength. Light and electrons and molecules are not obeying different rules that happen to look alike. They are obeying the same rule, summing over the same kinds of paths, and the only thing that changes from one to the next is how fast the little clock spins. And it does not stop at electrons. The same self-interference has been shown for neutrons, for whole atoms, and, most astonishingly, for large molecules containing dozens and then hundreds and eventually thousands of atoms. Objects big enough that you might think of them as tiny specks of solid matter, and yet they too, sent one at a time through a suitable arrangement of openings, build up interference patterns. There is a famous set of experiments in which molecules shaped like tiny soccer balls, each made of 60 carbon atoms, were sent through a grating and revealed their wave nature by interfering with themselves. If a molecule of 60 carbon atoms takes every path, then the line between the strange quantum world and the ordinary solid world is not where you thought it was. It is not that small things are quantum and large things are not. It is that everything is playing this game, and the reason you never notice it for a thrown baseball is something we are about to understand. Before we get there, I owe you an honest confession about the calculation we did, because intellectual honesty is worth more than a tidy story. Throughout, to keep things simple, we considered only the nearly straight paths, and we justified throwing away the wild ones by showing that they cancel. That justification is real, but the full, rigorous version of Feynman's idea does not throw anything away. In the complete treatment, you genuinely sum over an infinite collection of paths, including the wildly curved ones, the ones that double back, the ones no sane person would draw. The straight-line simplification we used captures the essential physics and gives the right answer because the wild paths really do cancel, but the true mathematical object underneath is a sum over infinitely many histories, an integral over every conceivable route the particle could take. That is why the full idea is called the path integral, or the sum over histories. What we did was a faithful shadow of it, accurate enough to build a wall of light and dark, but the real thing is even more extravagant than the picture we drew. And that extravagant real thing turned out to be one of the most important tools in all of physics. Feynman developed this formulation in the 1940s, building on an earlier hint from Dirac, and at first it looked like a curious alternative way to do quantum mechanics, a different route to answers people could already get by other means. But it grew into something far larger. When physicists went on to describe not just single particles but fields, the electromagnetic field, the fields of the fundamental forces, the fields whose vibrations are the particles of the standard model, they found that the sum over paths idea generalized into a sum over all possible histories of the field, and that this was the natural language for the whole enterprise. The theory of how light and matter interact, quantum electrodynamics, for which Feynman shared the Nobel Prize in 1965, is built on it. The standard model of particle physics, our deepest tested account of what everything is made of, is written in this language. The little spinning clock we attach to a photon's path to explain a laser on a wall grew up to become one of the central instruments for describing reality at its most fundamental level. There is even a sense in which people trying to understand gravity and the shape of space-time itself reach for the same idea, summing not over the paths of a particle, but over all the possible geometries the universe could have, an audacious extension of the very move we watched with the photon and the slit. Whether that program will succeed is unknown, an open frontier, one of the places where physics genuinely does not yet have the answer. But the fact that the reach even extends that far tells you how far the idea reaches. What began as a way to compute where a lonely grain of light would land became a way of thinking about matter, about forces, about fields, and perhaps about the fabric of space and time. So the pattern on the wall was never the point, it was the doorway. Behind it is a picture in which everything that moves, from a photon to an electron to a molecule of 1,000 atoms to, just possibly, the geometry of the cosmos, gets from here to there, not by choosing a path, but by exploring all of them and letting the arrows decide. And that picture leaves us with one last question, the one that has been waiting patiently since the beginning. If everything takes every path, then why does the world we actually live in, the world of thrown balls and straight beams, and objects that plainly go one way, look so stubbornly, reliably single track? Why does the everywhere at once hide itself so completely at the scale of a human life? The answer ties the whole story together, and it reaches back to a principle physicists had been staring at for centuries without knowing what it truly meant. Part 12. The residue of everywhere. For more than 200 years before Feynman, physicists knew a strange and beautiful fact about the world, and they could use it, but they could not say why it was true. The fact is called the principle of least action, and in rough terms it says this: when an object moves from one place to another, out of all the paths it could take, the one it actually follows is the one that makes a certain quantity, called the action, as small as it can be, or more precisely, the one where the action stops changing if you nudge the path a little. Throw a ball, and of all the arcs it might trace, it follows the one special arc that makes the action stationary. Light bending as it passes from air into water bends by exactly the amount that makes its action stationary. This principle works with astonishing generality. You can derive huge swaths of physics from it. But it always carried a whiff of the mysterious, almost the mystical. How does the ball know, at the moment it leaves your hand, which arc will turn out to have the special action? How does it survey the alternatives it does not take? For centuries, the principle was a magnificent tool that nobody could quite explain. Feynman's arrows explain it, and the explanation is the deepest thing in this whole story. Remember what we found about which paths survive the sum. The paths that reinforce, the ones whose little clocks agree and build a long resultant, are the paths clustered around the one where the length, and therefore the travel time, barely changes when you nudge the path. Near that special path, neighboring paths have nearly identical clocks, so they add up instead of cancelling. Far from it, the clocks disagree and cancel. And that special path, the one where small changes stop mattering, the one whose neighbours agree, is precisely the path of stationary action. The very path the principle of least action singles out. The classical path is not chosen by the ball or the light. It is the path that survives the quantum sum, because it is the one place where all the neighbouring histories agree instead of cancelling. So the ancient mystical-sounding principle turns out to be a shadow of the arrows. The ball does not survey its options and cleverly pick the least action arc. The ball, like everything else, takes every arc, and all of them interfere, and every arc cancels against its neighbours, except the ones clustered around the stationary path. And that surviving bundle is what we see and call the trajectory. Least action was quantum mechanics all along, seen from the far side, before anyone knew the arrows were there. What looked like the ball knowing the future was really the ball exploring everything and only the agreement surviving. There is a genuine intellectual thrill in this that is worth sitting with, because it is the kind of thing that does not happen often even in physics. For roughly 2 centuries, some of the finest minds who ever lived used the principle of least action as a master key, deriving the motion of planets and pendulums and light and fields from it. And they used it because it worked, not because they understood it. It sat at the foundation of the science with a faintly embarrassing air of magic about it. This business of the object somehow selecting the optimal path. And then, from an apparently unrelated direction, from the effort to understand a single photon building a pattern on a wall, came an explanation that dissolved the magic completely. The optimal path is optimal because it is the one whose neighbours agree, and agreement is what survives a sum over everything. The principle nobody could justify turned out to be a direct consequence of the arrows nobody yet knew to draw. When a 200-year-old mystery falls out for free as a side effect of a new idea, that is one of the surest signs the new idea has touched something true. It also quietly reverses the direction of explanation in a way that is worth making explicit. Before, you might have said that the classical world is the real, solid foundation, and the quantum world is a strange correction that shows up only when things get very small. Feynman's picture turns that on its head. The quantum sum over paths is the foundation, the thing that is always true, for the ball and the photon and the electron alike. And the classical world, the world of single definite trajectories and least action and sharp predictable motion, is not the foundation at all. It is what the quantum sum looks like when the objects are large enough that the cancellation becomes total. Classical physics is not the bedrock beneath quantum physics. It is the surface quantum physics wears at human scale, the residue left when the arrows for all but one narrow bundle of paths have erased themselves. You do not build the quantum from the classical by adding strangeness. You build the classical from the quantum by adding size and watching the everywhere disappear. Now we can finally answer why the everywhere at once hides from you. The clock's spinning rate is set by a quantity involving Planck's constant, the tiny number that sets the scale of all quantum effects, and because that number is so extraordinarily small, the clocks spin incredibly fast for any ordinary object. For anything as large as a thrown ball, the clocks along paths even slightly different from the classical one spin so wildly out of step that they cancel with ferocious completeness, leaving a surviving bundle so impossibly narrow that the ball appears to follow one exact line with no fuzziness at all. The everywhere is still there. The ball still takes every path, but the cancellation is so total that the surviving bundle is a single sharp trajectory, and the quantum haze is squeezed down below anything you could ever detect. Shrink the object down toward the scale of a photon or an electron, and the surviving bundle widens, the cancellation loosens, and the everywhere leaks back into view as bands of light and dark on a wall. The line between quantum and classical is not a wall between two kinds of stuff. It is just how wide the surviving bundle is, and that depends on how small you are. Return, now, to the sentence we have carried since the beginning, and feel how much weight it holds. Light takes every path, and only the agreement survives. When we first said it, it was a provocation, a strange claim about a laser and a slit. Now it is something much larger. It is the reason the classical world looks the way it does. It is the reason a ball flies in an arc, and a beam runs straight, and a molecule of 1,000 atoms mostly behaves itself. The definite, single-track, reliable world you move through is not the real truth underneath the quantum haze. It is the residue of the haze, the thin, surviving trace of a sum over everything, the places where the arrows happened to agree. Reality does not lay down one line and send things along it. It takes every line and shows you only what is left when the rest cancels out. The straight path, the sensible path, the path your whole intuition is built on, was never the thing nature chose. It was the thing that failed to erase itself. And the little clock, the homely spinning watch we gave to every path, turns out to have been the machinery of quantum mechanics itself, wearing a child's disguise. That same spinning arrow, dressed in Euler's elegant formula, runs through the equations of quantum electrodynamics and the Standard Model. It is what physicists are really summing when they compute how particles scatter, how light and matter touch, how the fundamental fields evolve. We drew it as a cartoon on a path between a slit and a wall, and it was the real thing all along, the arrow that remembers only the agreement. There is a caution worth keeping, spoken in the channel's usual honest register. The path integral is not the final word. It is one of several ways to express quantum mechanics. And physicists still argue about what it means for the photon to literally take every path, whether that is a description of what happens or an extraordinarily accurate way of bookkeeping. Some read the sum over histories as real, the particle genuinely exploring all routes. Others treat the intermediate paths as terms in a calculation rather than events in the world. And a few build the same predictions on entirely different pictures, a definite trajectory guided by a wave that passes through both slits. They all agree on every number, on exactly where the light lands, and they disagree on what is really happening underneath. Physics can compute the world to a precision beyond imagining, while still, honestly, arguing about what the computation is telling us. That is not a failure. It is the shape of the frontier, and it is where the wonder lives. Feynman himself, who gave us these arrows, seemed at peace with that unfinished quality, and he closed the very lesson these ideas come from with a line that is a good place for us to rest as well. He said he would rather have questions that cannot be answered than answers that cannot be questioned. So here is where we leave it tonight. You shine a red laser through a single narrow slit, and bands of light and dark bloom on the wall, and the reason is that the light and the electron and the molecule, and perhaps everything there is, gets from one place to another, not by taking a path, but by taking every path, carrying a little spinning clock along each one, and letting all those clocks add up. The world you see, calm and straight and single track, is the quiet residue of an everywhere you will never watch directly. And somewhere in the room around you, right now, the light is doing it, going every way at once, and only the agreement is reaching your eyes.